Hey kid, binary trees don't suck. In fact, they're very easy to learn. And because I'm such a cool and awesome guy, I'm going to teach you today something about binary tree insertions. Binary trees must always remain balanced. To determine whether a binary tree is balanced or not, we need to find its balance factor. The balance factor of a binary tree is given by the equation height of left subtree minus height of right subtree. Given this binary tree, what is its balance factor? Since the height of the left subtree is 0 and the height of the right subtree is 0, the balance factor of this tree is 0. How about this binary tree? Since the height of the left subtree is 1 and the height of the right subtree is 0, the balance factor of this tree is 1. Finally, what about this binary? Since the height of the left subtree is 0 and the height of the right subtree is 1, its balance factor is -1. Now that you know how to solve for balance factors, you may have been wondering what balance factors are for. Remember that binary trees should always be balanced. Therefore, a binary tree's balance factors should always be greater than or equal to -1 and less than or equal to 1. So what do we do when we have unbalanced binary trees? We rotate them. There are 4 basic types of rotations. The first type of rotation is called the left rotation. As you can notice, this is a right-skewed binary tree and it has a balance factor of -2, which means that this binary tree is unbalanced. We are going to perform the left rotation on it by moving node A down and moving node B up, so that at the end, we have a binary tree looking like this. Now it is balanced. The second type of rotation is called the right rotation. As you can notice, this binary tree is a left-skewed binary tree and has a balance factor of 2. We're going to perform the right rotation on it by moving node C down and moving node B up to the right, so that at the end, we have a balanced binary tree looking like this. Its balance factor now is 0. The third type of rotation is called the left-right rotation. It is a combination of the left and right rotation. As you can notice, this binary tree has a balance factor of 2. We are going to perform the left-right rotation on it by first moving node A down and then moving node B up, so that we have a binary tree looking like this. However, this new binary tree's balance factor is still 2. Therefore, we need to perform one more rotation on it by moving node C down and then moving node B up, so that we finally have a balanced binary tree looking like this. Whose balance factor is now 0. The fourth type of rotation is called the right-left rotation. It is a combination of the right and left rotations. As you can notice, this binary tree has a balance factor of -2. We are going to perform the right-left rotation on it by first moving node C down and then moving node B up to have a binary tree looking like this. However, this binary tree also has a balance factor of -2. Therefore, we need to perform one more rotation by moving node A down and then moving node B up, so that we have a binary tree looking like this. This binary tree is now balanced and has a balance factor of 0. Now that we know how to rotate with binary trees, we can now create our own binary trees given a set of numbers. Let's say we are given this set of numbers and asked to create a binary tree from it. We need to start with the first number given in the set. In this case, it is 6. We then add the next number, which is 8. Since 8 is greater than 6, we put it to the right of 6. The next number is 7. Since 7 is less than 8, we put it to the left of 8. Now, our binary tree's balance factor is negative 2. That means we have to rotate. Now our binary tree's balance factor is again 0. We then move on to the next number, which is 4. Since 4 is less than 6, we put it to the left of 6. The next number is 5. 5 is greater than 4, 5 at the right of 4. Again, the balance factor of 6 is 2. So we have to rotate at 6. Now our binary tree's balance factor is 1, which is okay. We then move on to the next number in the set, which is 2. 2 is less than 4, so it is placed at the left of 4. The next number is 1. Since it is less than 2, it is placed to the left of 2. Now the balance factor of 4 is 2. That means we have to rotate at 4. However, the balance factor of 7 is now 2. That means we have to rotate at 7. Node 6 gets adopted by 7. Now our binary tree's balance factor is back to 0. We now move on to the next node, which is number 9. Since 9 is greater than 8, we put it to the right of 8. The next node is number 10. Since 10 is greater than 9, we put it to the right of 9. However, the balance factor of node 8 is now negative 2. That means we have to rotate at 8. There are no more numbers left in the list, and the balance factor of our binary tree is within the range of -1 to 1. That means we have created the first ever binary tree.